Start recording. There we go. All right. Page 59. Do I have a glove? Where's my glove? I don't have a glove? No. That's no good. There's one. Okay. When mixing a strong acid and a strong base, the two will neutralize one another. Is it going to be a one-way arrow or a two-way arrow? It's going to be a one-way arrow. If you have a strong acid and a strong base, you end up, of course, like any acid base, you end up with a salt plus water. And if this was a strong acid, and this is a strong base, neither ion will hydrolyze in the salt. Why is that? It's because you're going to have a metal hydroxide, yeah? And it's got to be a soluble one, so it's not going to be chromium, iron, or what's the other one? Chromium, iron, or aluminum, because those ones are not soluble with hydroxide. Unless you have NH4OH, but that seems rather unlikely, okay? So you're always going to have like a metal, and we know that metals do not hydrolyze unless it's one of those three. And your strong acid, that is the conjugate acid of whatever the negative ion is. And if your conjugate acid is strong, it will not hydrolyze. So, good rule of thumb, if you have a strong, you end up with a salt and water, neither will hydrolyze. And if you make it to completely neutralized, what will the pH be?
7.
It's going to be 7. Okay, so if neither the acid nor the base neither the acid nor the base are in excess, you're going to have a neutral solution. If you have excess acid, in other words, you've got excess H+, it's going to be acidic. Does that make sense? Hopefully. And if you have excess base, excess OH-, your pH is going to be greater than 7. It's going to be basic, and I need to fix that because that needs to be a lowercase p. Fix. All right, so if we ask ourselves, what is the resulting pH when we have 10 milliliters of 0.1 molar hydrochloric acid, and it is mixed with 10 milliliters of 0.10 molar NaOH. Can anyone tell me right off the bat what the pH is going to be?
7.
It's going to be 7 because the volume and the concentration of both of them are the same. You can do the calculation and you can say, okay, I've got my moles of HCl. Do you remember what of means? Of means multiply. Times. So you take 10 milliliters, 0.01 liters, and you multiply by 0.10 moles of HCl per liter. And then there's 0.1 mole, and then there's 1 mole of hydrogen per mole of HCl. The only reason to show this is that we're going to be doing this calculation a lot. So this is how much H plus we start with. Moles of OH, we calculate exactly the same way, and the calculation is exactly the same. We have 10 milliliters times 0.1 mole per liter times 1 mole of OH per 1 mole of NaOH, and we get same number of moles of OH minus at the start. It wouldn't actually be necessary to do anything more than this than to say, here we are, the solution is neutral. But just so you are familiar with this new technique we're going to be using, I have not got a nice name for this one. We've had rice tables, yes? What does R stand for?
Reaction.
I,
Initial.
C, change, E, equilibrium.
Oh, I was reading the F.
Now we are going to change the equilibrium because this is not an equilibrium, it is a one-way arrow. So instead of equilibrium, it's going to be final. And instead of doing concentration, we are going to do moles. So it's going to be moles, not molar. And it's going to be final, not equilibrium. So there's no really good name for this. I call it a RICFA table, which is sad, but there we are. Okay? It's a RICFA table. Learn to love it. I will say it often. It's almost so bad that it's good, but not quite. All right. So if we start with, remember this is our start, 0.0010 moles of H, 0.0010 moles of H. And we have 0.0010 moles of OH, 0.0010 moles of OH. Whichever one, because these are 1-to-1, whichever one is the smaller one is going to get completely used up. Now, because they are both the same, they are both going to get completely used up. So how much are we using up? We're using up all of it, 0.0010. We're using up 0.0010. So we are left with 0 and 0 moles.
How like molar we have to convert it.
Yes, for this one, because what's happening is your final concentration is going to be the moles left over in the total volume. So you're going to have to calculate a new concentration because there's now a mixture with the total volume. Okay, and in this case, yay, we have some water and that's it. Okay, and so it doesn't matter because this means nothing. This whole table is not necessary for this question. I can't imagine this being anything other than a multiple choice question where you go, moles of H equal moles of OH. It's pH 7. Okay, but we've seen the new tool, the RICFA table. So let us try 10 milliliters of 0.100 molar HCl. And we're adding that to 90 milliliters of 0.100 molar NaOH. And I'm going to work in millimoles. If you hate this, you can work in regular moles. But it is faster and the numbers are more pretty if you work in millimoles. You'll end up with numbers like 5 instead of 0.005. Yes? Just nicer numbers. So I have 10 milliliters of times 0.1 moles of HCl, and there's 1 H for every 1 HCl. So we have 1 millimole. Isn't 1 a nice number? Isn't it nicer than 0.001? Okay, so that's why we do that. Now, because this milli is here, we have millimoles instead. If you don't like it, like I said, you can not use milli and just have 0.001. OH, we have 90 milliliters of, remember of is times, 0.1 moles of NaOH per liter, and then there's 1 mole of OH per 1 mole of NaOH. And so we get 9 millimoles of OH. 9 is a nice number. Our net ionic equation, when we take HCl plus NaOH goes to H2O plus NaCl. If we wrote our complete ionic equation for that, what would we get? This is our formula equation. H plus Cl minus plus Na plus OH minus goes to H2O plus Na plus Cl minus. And if we want then our net ionic equation, what would we cancel out? The Cl and the Na. And so what we're left with is H plus OH minus gives H2O. That is the net ionic equation for every single strong acid, strong base reaction. Okay, this is the net ionic equation for every strong acid, strong base. I'm going to get used to seeing this abbreviation because we're going to have SB, WB, SA, WA, strong acid, strong base, weak acid, weak base, that kind of thing, because it gets tiring writing them out all the time. So every time you do a mixture of a strong acid and a strong base, your equation is going to look like this. There is no, I mean, you can do it with the other stuff, but there's no real point because you're interested in how much H is left in excess or how much OH is left in excess. So we start with, and remember I am putting millimoles here, but if you don't want to put it over there, you can put millimoles and millimoles. It doesn't matter as long as you put it somewhere.
Isn't this the rice?
This is our RICFA table, but we're not there yet. We're just doing the RI, okay? And we're going to look at the RI, and we got 0 water. Which reactant is going to get used up completely?
Both of them.
I have 1 mole of this and 9 moles of that. The H is going to get used up completely. That means it is our limiting reactant. So that's our H plus. Which one is going to have some left over? OH minus. And the millimoles, use the millimoles of limiting reactant as the change, because how much is going to get used up? 1 millimole is going to get used up, right? So H is all going to get used up, all of it. This is a 1-to-1 ratio here, so this is also going to be 1 millimole getting used. H goes from 1, you take away 1 and you get 0. OH, you start with 9 millimoles. You take away 1 millimole, and you're left with 8 millimoles in excess. There are 8 millimoles of OH minus left over. Yes? Do you have to do the RICFA table to figure this out? No, you don't, but I have found that lots of students find it helpful in just organizing their thoughts, okay? So if you don't like it and you can show your work clearly without it, that is okay, but I've found that most people find it helpful, so I'm gonna stick with it, okay? Now that we know we have 8 millimoles of OH, we have to take our millimoles of OH, and we have to then find concentration of OH, and then we have to find POH, and then we have to find pH to find the pH of this solution. Yes? So our concentration of OH, we're going to take our moles of OH over our total volume. Well, because we are working in millimoles, our volume can be in milliliters. Do you see how that's sorting itself out now and we don't have to worry about it? If you kept it just as regular moles, you would just divide by regular liters. Okay? So we have 8 millimoles, and our total volume is 10 and 90. Oh, we were going to get you to erase the board because I'm too short.
Because you're a really big, tall, independent.
If you're too short, you can use this rolly thing too, but I think you'll probably find everyone other than me in this universe is fine, mostly. I also, in addition to being short, I also have very short limbs. I'm like the Tyrannosaurus Rex of people, right? Anyway. When I drive my car, I have to be like this. Like, anyway, it's really bad. I'm like, okay. They're always like, bring your shoulders back. And I'm like, but then I can't reach anything. Okay, anyway. All right, so where were we? We had 10 milliliters and 90 milliliters as our total volume. So we have 8 millimoles left over in that total mixture, which is 10 plus 90, that's 100 milliliters. 8 millimoles divided by 100 milliliters. Yes. Yes, please. Everything. Great. See, that was so much better than me doing it. Thank you. And we get 0.0800 molar OH minus. Now the question asks, what is the pH? So of course, then we just go through what we usually go through. And you guys are so good at this now. We're just going to be like, find the POH, find the pH, and then check your sig figs. Or you can take your OH and go to H, and then pH, and then check your sig figs. It should be 3 sig figs. Do you see how that's 3 sig figs? That's our pH. Are we good with that being 3 sig figs? Okay. Excellent. Do you guys want to try the first one?
The brackets.
Brackets. Blah, blah, blah. Plus blah, blah, blah. Close bracket.
Okay. So it's basically has yo. You figured once to start.
HCl.
Oh, no.
Right, because you say 50 milliliters of that, so that one, that.
Let's do this.
You can make. Yeah. I know, right? Like, I was expecting. Oh. So that. It's so hard. Oh, yeah. Not right, we'll take on that, yes.
Other filters out.
You know?
Cancel.
Oh,
Oh, yeah. Oh, yeah. So the L cancel the L, so it-
And the M cancel, yes, it does.
I feel so smart now.
Oh, I see.
Yeah, stage five.
Yes. Yes.
That's not point two.
Six fix 10.0.
Hmm?
How's the six fix 10.0?
Because I've got 3 and 3.
Oh.
Yeah. You don't really even need to do the water. Like, it's kind of irrelevant. So if you leave out the water, it's not the biggest deal. Do you know what I mean? Like, do you? Yes, because I cannot math. Now, question, is the hydrogen 2.5 or is it 2.50? Our uncertain digit is the 0.1 position, right? That's our first uncertain digit. So we are now down to how many sig figs? 2 sig figs. You have to watch out. There are subtractions taking place here. So you can start with 3 sig figs and end up with a smaller number. Yeah? Might not happen, might happen. You just have to be aware of it. Oh, and I should really write millimoles in here. Millimoles, millimoles. That way I don't have to write it for every single number. So I have 2.5 millimoles in 100 milliliters. And so now we have 2 sig figs there. Yeah? Is good? I'm going to leave the second exercise for you to do at home if you haven't already done it on your own. And we're going to move on. I don't know why I made this 2 worksheets. They could have just made it 1 and had that be an example. So now we're going to go to 5.4b, which maybe just should have been the same thing. Like I said, I don't really know why. So the only thing that's different here is that instead of having just an OH, we have an OH2. Yeah? So when we calculate the millimoles of OH, we need to take that 2 into account. Okay? So we have HCl plus BaOH2 gives Ba plus Ba2 plus H2O. These are all aqueous. If we balance that, that gives us 2 HCl and 2 H2O. And then if we make that our complete ionic equation, we split that up, we get 2 HCl's and 2 H's, 2 Cl's, 2 bariums, 2 hydroxides, 1 barium, 2 hydroxides, 1 barium, 1 chloride, and a water. The water stays together. Now, our net ionic equation, we will cancel out any spectators. Who are the spectators in the, whoa, where'd it go? Who are the spectators in this, why is it doing that? It's jumping all over the place in this reaction. Who are the spectators? Ba and 2Cl. And guess what? We get 2 H's, we get 2 OH's, and we get 2 water, which simplifies down to H plus OH minus gives H2O. Is that not what I promised that every single net ionic equation for every single strong acid base would be? So it's no different. The net ionic equation is no different. The only thing that's different is that if you had 1 molar barium hydroxide, you would have 2 molar hydroxide, and that's it. Okay, so you would again calculate the moles of H. So you would say I have 50 milliliters of times 0.2 molar. That gives us 10 millimolar H plus. And then calculating OH, in this case, we have our 3 molar barium hydroxide. In this case, we've got 2 moles of OH per 1 mole of barium hydroxide. The other way to do it would be to say, if you wanted to, you could say that gives us 0.600 molar OH minus, and then just calculate it with the OH minus. Either way is fine. Does that make sense? Okay. As long as you've got that in there somewhere. And then, is it any different than before? No, we have 30 millimoles and we have 10 millimoles. We put those up at our top. Water is 0. Who's the limiting reactant? H plus. So we're going to use 10 millimoles of each of them. And so we're left with 20 millimoles of OH in excess. And that's what we get. And there's some exercises here. And again, I'm going to leave you to do those. And we're going to move on. Okay. Now we get into the complicated stuff. Weak acid plus strong base, weak base plus strong acid. So this is weak acid, strong base, and this is weak base, strong acid. I'm never going to ask you to put together a weak acid and a weak base because it will not go to completion. But as long as you have one strong thing, it will go to completion. One strong reactant goes to completion. Because basically what's going to happen is if I'm a strong acid, right, and I've got all my hydrogens, just pretend I'm a whole bunch of different strong acid molecules, and you guys are all weak bases, I'm going to be like, hello, weak base, here. Hello, weak base, here. Hello, weak base, here. Hello, weak base, here. Am I taking any of them back? I was a strong acid. Does my conjugate base accept protons? No. So is that going to completion? Yes. Thank you. Okay, so when a weak acid is partially neutralized, in other words, before the equivalence point. So do you guys remember what an equivalence point is? The equivalence point is where there is no excess of either reactant. It means that the stoichiometry is perfectly fulfilled. If the reaction is 1-to-1, I gave you 1 mole of this and 1 mole of that. Or I gave you 0.7 moles of this and 0.7 moles of that. They are 1-to-1, they react completely, we're done. We've got no reactant left. But here we are saying we are not at the equivalence point, we are before the equivalence point. And we have we have our strong base. Here's our strong base, our SB. And oh, my base should be blue, shouldn't it? Let's make base blue. There's our strong base. Our weak acid is there. So we are mixing NaOH and acetic acid CH3COOH. Could you please predict the products of that reaction? Oops. Is that what you guys got? Okay. Could you please write that now as the complete ionic equation? And remember, are weak acids mostly apart or mostly together? Weak acids are mostly together. What? That's why their Ka's are little. Yeah? So when we write the net of the complete ionic, we do not take them apart. We keep them together. Weak stays together. And then if we get our net ionic equation, who's going to cancel out? Na plus, CH3COO, NaCH3COO. NaCH3COO comes, separates out.
Na and no.
How about just Na? Everything else is different, right? Okay, so what we've got then, for our net ionic equation, we just have OH minus plus CH3 COOH goes to CH3 COO minus plus H2O. And that is a one-way arrow. Why is that a one-way arrow?
Because it's a strong base.
One way because NaOH is a strong base. Now that we are here, we can do this just like we did for the other questions. We can find our millimoles of this, we can find our millimoles of that, and we can do a Rikva table. So, oh, did I not leave a place to find our millimoles of NaOH? I did not. That was silly. Millimoles of OH minus 2 milliliters times, oh, I see why I didn't, because it's like really easy math. 1 mole per liter. And that gives us 2 millimoles of OH minus. So that is 2.00. We're going to get a little lazy here because I don't have any room to write this. How many millimoles of acetic acid? That's in our pink there. 8. Can we just go with 8 and not show the calculation for today? Okay. Okay, so we got 8.00. And don't forget, you'll want to write millimoles here so we know that's what we're dealing with. And how much of our products do we start with? 0, as always. It's 1-to-1 who gets used up completely. The OH, so that's going to go down by 2.00. This one's going to go down by how much? 2.00. And this one's going to go up by 2.00. And we don't care about water. So this is going to end up being nothing. This ends up being 6. And this one ends up being 2. So now what we've got is we have a weak acid and we have its conjugate weak base. All right, so now we have our millimoles of acetic acid, 6.00 millimoles. What's our total volume? 2 plus 8 is 10. Okay. In 10 milliliters gives us 0.6 molar. Acetate is, what's acetate? 2 millimoles, not milliliters, millimoles. In 10 milliliters is 0.200 molar. So we have weak acid and weak base left after the reaction. So it doesn't matter whether you use the weak acid or the weak base equilibrium equation. But if you use the weak acid equilibrium equation, you can use the Ka from the table. If you use the weak base, you have to then calculate Kb from the value on the table. Which one sounds like less work? Using the acid or the base?
The base, because it gives us the acid way now.
If you use the acid form of the equation, so if we write our weak acid equilibrium, CH3COOH, because this is what we've got, right? And it's in water. We get CH3COO minus plus H3O plus. That's our weak acid equilibrium. And that means we're going to use a Ka. Where do we find the value for Ka? This is from the table. Now, if we did the base form of the equilibrium, would we be able to look up Kb on the table? No, we would have to do a calculation for it. Do we like doing more calculations? No, so I would recommend always using the acid form. Now, this is a little bit different because normally we start with only reactants, right? But in this case, we have some reactant, and we also have some product. Yes? So we're going to put our 0.600 here, and we're going to put our 0.200 here. And how much H3O plus do we start with?
Wait, how is the initial of that one?
Okay, so what has happened is we took some NaOH, yes? We took some NaOH and we took some acetic acid, yes? The problem with this is you have to keep in mind that two things are going to happen, okay? Two things happen. We have the neutralization. That's number one. And in the neutralization reaction, we end up with six molar acetic acid and, sorry, 0.6 molar acetic acid and 0.2 molar acetate. That's part one. Okay. Now, does step two, weak acid equilibrium. So we made this much and this much. Yes, we made that much and that much, 0.6 and 0.2. And now those two are going to react with each other. Does this all actually happen all at once? Yes, it does. But if we're doing it on paper, we can say step one, neutralization. Oh, pause, take a breath. Initially, the initial values for step part two, which is these two equilibrating with each other, them coming to an equilibrium, because right now they're not at an equilibrium. Right now they're at whatever this is. Okay, so we start with none of that. Because what did we make? We made acetic acid, we made acetate ion, and we did not make any H3O plus. Yeah? So that's what we're starting with, and now it just becomes a rice table like any other rice table, except that we've got something on both sides. But which way does it have to shift? Remember, this is 0. So this has to go up. You cannot go down from 0. Yeah? Have to shift right. That means this is also going to go up, and that means that this side is going to go down. How much are they going to go up and down by? No clue. Ah, look at that, X. No clue, unknown. So now we have 0.600 minus X, 0.200 plus X, and X. Yes? We have made H3O plus. So we're going to write a Ka expression. You could write this as H3O plus if you wanted to, or you can just write it as H plus. It doesn't really matter. Okay. Thank you.
Now, sorry.
It is being recorded. The real essence is being recorded.
What is the impact?
Okay. So now what we do is we say, okay, I have our Ka value from the table. We have hydrogen, which is X. We have 0.200 minus plus X. And we have 0.600 minus X. Oh my gosh, that looks horrible. Doesn't that look horrible? Does that look like it's going to be nasty to solve? Well, let us assume that this X here and this X here are insignificant. And if that's the case, that simplifies it right down. Now we just have X times 0.2 over 0.6 equals 1.8 times 10 to the minus 5. And that gives us X is equal to 2.4 times 10 to the minus 5. And that gives us a pH of 4.27. You'll notice I'm getting really sloppy with my showing work for pH. Okay. And that's because I know you guys know how to do that part, right? Everybody knows how to find a pH at this point, right? So how much fun was that? You're like, yeah, so much fun. Okay. So that's before equivalence point. Exactly halfway to the equivalence point. What's the equivalence point? Tell your partner, what is the equivalence point? So that's the point where all the H plus and all the OH minus are reacted. There's no excess of either. That's our equivalence point. And in this case, instead of H plus, it's going to be CH3COOH because the H is still attached to the acid. Are we okay with that? Yeah, okay. There is a special point when we're reacting with an acid with a base, and that is where exactly half of the weak acid is neutralized. Exactly half of the weak acid is neutralized. We call that the half equivalence point. When all the weak acid is neutralized, we call that the equivalence point. When we're halfway there, we call that the half equivalence point. So, for example, here we have our strong base. We have 2 mils of 1 molar. So that is 2 mils of 1 molar is 2 millimoles. Yes? You'll notice I'm playing fast and loose with my sig figs here because I just want it to be like really, like I want you to focus in on what the numbers are rather than how many digits there are, because this is tricky enough without worrying too much about digits. And that's millimoles of OH minus. Why am I saying OH minus instead of NaOH? NaOH is the Na is a spectator. Now over here, we have 4 milliliters of, and remember that's 4 milliliters of 1 molar CH3COOH. And that's equal to how many millimoles? 4 millimoles. All right. So we know that we have 4 millimoles of CH3COOH. There it is right there, 4 moles of CH3COOH. We have 2 millimoles of hydroxide, 2 millimoles of hydroxide. Those react 1 to 1. So how much is going to get used up? 2 millimoles. So we are using up half of the acid. What do we call that point when we use up half of the weak acid? That's our half equivalence point. So all the OH minus gets used up, we're left with 0 molar. 2 millimoles of the weak acid gets used up, so we have 2 millimoles. And if this one goes down by 2 millimoles, then how much does its conjugate base go up by? 2 millimoles. Look, those numbers are the same. At the half equivalence point, the conjugate acid and the conjugate base millimoles are the same. And they're in the same volume, so the concentration of the acid and the conjugate base are the same. So here's our weak acid, and here is our conjugate weak base. How much do we have of each? We have 2 millimoles of each. Same. And that gives us, because they're in the same volume, that gives us the same concentration. Yes? So when we've neutralized half of the acid, we have exactly the same concentration of the acid form and of the base form of that weak acid. Yes? This is important because when you write a Ka, if this and this are equal,
If H plus is equal to
then Ka is equal to H plus, just like when we did it for the indicators. You remember how indicators, when the indicator HIN and IN minus were the same concentration, Ka was equal to H plus. At the half equivalence point, when we're reacting a strong acid with a strong base with a weak acid, then Ka is going to equal to H plus. So actually, if you are doing a titration of a weak acid plus a strong base, if you get halfway to the equivalence point, you can find the Ka of that strong acid, or the weak acid, sorry. So let us take our equilibrium here, and this is, could we have done a weak base equilibrium here? Because we have both the weak acid and the conjugate weak base, correct? We have both. Could we have done a weak base equilibrium here instead? Would that be okay? Yes, it would be. But we're not going to, because Ka is easier to find than Kb. So here's our weak acid equilibrium. You'll notice our equilibrium has both the acid form and the base form. Okay? And now we're not doing a Ricfa table anymore. Now we're doing a Rice table, because when you have a weak and a weak, that forms an equilibrium. So step one, neutralization. Step two, weak acid equilibrium. Step one, completion. Therefore, you're using a Ricfa table. Step two, it's an equilibrium. So you're going to use Rice. How much are we starting with for both of these? We are starting with 0.33 molar of each, right? Because these were the same. The hydrogen, though, is at 0. So which way do we have to shift? We have to shift towards the side with the 0. That means that has to go up. You cannot shift away from a 0. You cannot use up nothing. So we have plus x minus x. We end up with 0.33 minus x, x, and 0.33 plus x. If we chuck all of these into this expression here, we don't actually end up with beautiful cancelable numbers, because even though this and this are the same, we have a plus x on the top and a minus x on the bottom. But what are we going to do with those x's? We're going to assume they are really small, because if you think about it, those x's are to do with how much dissociates. And how much dissociates has to do with how big this number is. Is that a big number or a small number? 1.8 times 10 to the minus 5. That's a small number. So is very much going to dissociate compared to 0.33? No. Okay. So what we're going to do is we're going to assume X is much, much less than 0.333. And if that's the case, what do we do with those X's? We just ditch them. Bye-bye. And we say, these are the same. Yes? And so X, and remember what was X? X was the concentration of hydrogen. And what was this 1.8 times 10 to the minus 5? This was Ka. So we don't actually have to show all of this nonsense. We can just say that at the half equivalence point, Ka is equal to the concentration of H+. So at the half equivalence point, and the half equivalence point, we can represent that. This right here means concentration of H+ at the half equivalence point, halfway to being completely neutralized. But I don't want to write out H+ at the half equivalence point. So we just write concentration of H+ 1/2. Yes. H+ is equal to Ka, or you can say that pH 1/2 is equal to pKa. And really, out of all that horrible, complicated stuff that we did today, this is all you need to take away. Yes, all this horrible, complicated stuff, complicated. All you really need to know is, because quite frankly, am I going to give you this question? No, it takes too long. Yes, too long. Oh, but this one, look at that. Isn't that sweet? Yes? Okay. But we're not finished this yet. We still have to look at what happens if we use a weak base equilibrium. And then what if all the acid is neutralized? What happens when we're at the equivalence point? So we're not going to do anything with this today. Today you are going to do page 60. Let's write page 63. Number 1. Page 64. Number 2. And then I want you to start working on reviewing hydrolysis. So let's have you do. Oh, there's a lot here. Let's just have you do number 1, odd letters. Is there odd letters? Odd. Yeah. Number 1, odd letters on page 49. Okay, so not too much. If you want to go past that on any of these things, if you're like, oh, I feel like I'm getting it and I just need a little bit more to solidify, please feel free to go past. But that will at least give you a review of what we did, last weekend today. So there we are. Okay.